Hi, in this video we'll talk about elasticities. So we've been discussing how different factors might change demand and supply and also the equilibrium outcomes in price and quantity. However, not every change in a variable will bring about exactly the same change on demand and supply. For instance, an example we talked about before in terms of the company's demand for internet services. Small firms have very different demand compared to big firms, and small firms' demands are much more responsive to increase in price. In this particular example, in our slide here, the demand for pork may respond to the increase in price differently in slightly different markets. In one market, maybe when the price increases by 25 cents, the demand is going to change to some extent. But maybe in a different market, the demand does not change at all because people really like pork. In a third market here, it might be the scenario where when the price increases, the demand is going to change dramatically. So obviously, we need some kind of measure to help us gauge by how much will demand or supply change when a particular variable moves around. Well, you might say, then doesn't our derivative already answer that question for us? Well, the answer is partly yes, but sometimes we might want to use a slightly different measure, and that is elasticity. Elasticity is a measure of a percentage change in an outcome variable when another variable changes by 1%. So don't get freaked out by this particular expression for now, and I'll unpack this for you in a second. Before we go there, let me give you a particular example. For practical reasons, the $1 increase in the price of a product doesn't mean exactly the same thing across different products. For instance, a $1 increase in the price of one roll of toilet paper is a lot, whereas a $1 increase in your monthly rent is almost nothing. So if we want to compare how responsive demand is to changes in price, it is not always appropriate to just compare the response to a $1 increase or 1 unit increase. Rather, it is a more appropriate analysis to think about how much will demand for toilet paper change if there is a 1% increase in its price. So for toilet paper, it might be 2 cents, whereas for rent, a 1% increase in the price might be $20. So when we look at the response in demand across these two different products to 1% change in their respective prices, it's a much more reasonable comparison. There are also many technical reasons you will see throughout the course later on that elasticity is a very appealing object to work with in analysis for technical reasons. Now let me dive into this particular technical expression, and then hopefully we can gain a little bit of intuition from it. For any type of elasticity, the conceptual definition, as we've been discussing, is just a percentage response to a percentage change. So for instance, if we call the outcome variable z and the input variable x, then we're just saying if there's a 1% increase in x, how many percentages will change in z? Well, we can unpack this a little bit more. We can rewrite percentage change in z as the change in z, where delta means change, divided by the level of z at its base level. Let's say z increased from 100 to 101. Then the change will be 1, and the base level will be 100, and that 1 unit increase will be 1%. And similarly, the percentage change in x can be written as the change in x over the base of x. Now, once we have this expression, we can rewrite it a little bit. So instead of writing delta z over z divided by delta x over x, we're able to rewrite this as delta z over delta x times x over z. And that's our expression here on the right-hand side. Now, once you see this as a product of two different fractions, we can then ask, what if the change in x is really, really small? And as this change in x becomes infinitesimally small, the approximation to that change in x in response to infinitesimal change in x is the derivative of z with respect to x. In other words, a very close approximation to elasticity is in fact this particular expression. It is just a derivative multiplied by the ratio of the input over the output. And let's see how this works. A familiar concept you might have heard about in the principles economics class is a price elasticity of demand. We're interested in how much percentage will demand change when there's a 1% increase in price. Well, to calculate that, the conceptual definition is just changing demand over demand divided by changing price over price. But our operational definition from the previous slide is in fact that we can calculate this by using derivatives. It is just a derivative of the demand function with respect to price multiplied by the ratio of price to quantity demanded. And the interpretation is exactly the percentage response kind of definition we had. Similarly, we can calculate income elasticity of demand. This is also an important concept, where we measure how many percent will demand increase if there's a 1% increase in consumers' income level. We can calculate this expression similarly, which is just a derivative multiplied by the ratio between y to quantity demanded. In addition, as opposed to demand, we can think about the supply side as well. We can calculate the price elasticity of supply. In other words, how much will quantity supply increase if the price increased by 1%? Well, the calculation is, again, following exactly the same format, is going to be derivative of the supply function with respect to price times the ratio between price and quantity supply. Now, because these three expressions will be used repeatedly later on, we're going to put on some special notations on them, and we're going to use some very special Greek letters to reserve their positions. For price elasticity of demand, we're going to use a Greek letter epsilon. For income elasticity of demand, we're going to use the Greek letter xi. And for price elasticity of supply, we're going to use the Greek letter eta. In addition to these three elasticities, another elasticity you might come across in many different places is the notion of cross-price elasticity of demand. And this notion is to say that if price of one product increased by 1%, how will the demand of a different product respond to that? For instance, in our previous example, if there's a $1 increase in price of beef, then the demand for processed pork is going to change. But what is the percentage response in the demand of processed pork in response to a 1% increase in price of beef? Well, that is measured by a cross-price elasticity of demand. Here, we're just writing the expression as it's a percentage change in the quantity demanded for one product responding to the 1% increase in a price of another product. A little O here in the subscript is there to indicate that this is another product. Now, having seen the definition of different variations of elasticities, let's take a look use an example of price elasticity of demand and see how this definition of elasticity works through a very simple linear demand function. Now let's look at a general linear demand function that takes the form of QD is equal to A minus BP, where A and B are just some positive constants. So from this function, we can see that if P is 0, then the quantity demanded is going to be A units. And for every extra dollar increase in the price of this product, the quantity demanded is going to decrease by B units. So how do we calculate the price elasticity of demand for this particular demand function? Well, remember, the operating definition of price elasticity of demand only has two components. The first component is a derivative of the quantity with respect to the variable that you're interested in this case, price. And then we're going to multiply the ratio of the factor, which is price here, over the outcome variable, which here is quantity. So to do that, we're just going to take the derivative first and find out the first component. Now we're going to take the derivative of quantity demanded with respect to price. And that derivative is very straightforward because here A and B are simply constants, we're taking a partial derivative with respect to price. In other words, we're only varying price by a little bit and then see how quantity demanded will respond to it. And then the outcome is minus B, exactly as our intuition by looking at this demand function. Now, because we already have the derivative in place, we can simply plug this result into the definition of elasticity and then multiply it by the ratio of price, which is the factor that's causing the change, to the outcome variable, which is quantity demanded here. Now, using this definition, we'll just plug in this quantity here that we found in step 1, which is minus B here, multiplied by price over quantity demanded. And that's it. This is our price elasticity of demand for this linear demand function. Now, what we would like to do is take a closer look at this result, and then to learn a little bit extra insight from the observations. First of all, notice that the derivative of QD with respect to P carries a very natural interpretation. We know that it is the quantitative response in quantity demanded coming from 1 unit increase in price. In addition, graphically, the interpretation is that this derivative is equal to 1 over the slope of the demand curve. And it is 1 over because when we plot the demand and supply curves, again, we're plotting the factor, or P here, on the vertical axis. So in fact, we're inversing the demand and supply function first and then plotting them. And the result of that is that the slope of the curves are the inverse of the derivative of the demand and supply functions themselves. Now focus on this particular expression of elasticity, and remembering that minus B is simply 1 over the slope of the demand curve. Then what we realize is, in fact, for linear demand, although the slope of the demand function is constant, however, the price elasticity of demand for a linear demand function is not a constant. And the reason is the following. By looking at this expression of elasticity here, we have a constant non-changing slope in the front, or rather, really 1 over the slope. And it's being multiplied by this ratio of P over QD. If we pay a closer attention of the linear demand function, what we'll realize is in fact that although the slope is always at 1 over B, but the ratio of P over QD is not constant. So how does the ratio of P over QD change? Let's take a look at a particular graph here. Take any general linear demand function here, like this. We can look at how the ratio of P over Q changes. Imagine that we are starting from on the Q-intercept, and we start to slowly ride along this linear demand curve upwards. And let's think about how the ratio of P over Q changes. When we're at the Q-intercept, what is the ratio of P over Q? Well, at this intercept, P is going to be 0, and Q is going to be some large positive number. So the ratio is going to be 0. Now, let's skip to the end of this travel to the P-intercept. Once we reach the P-intercept, what is going to be the ratio of P over Q? Well, now we don't really know what the value of P is, but it's going to be some large positive number. And what is the value for Q? It's almost 0. In fact, at the P-intercept, what happens is we're dividing a positive value of P by a value of Q, which is almost 0. And the result of that is infinity. Now, how does the value of P over Q, or the ratio of P over Q, change from the Q-intercept all the way up here to the P-intercept that is infinity? Well, it changes continuously in the following sense. As we travel up this demand curve, what happens is our value of P kept increasing, while the value of Q kept decreasing. So, as a result, the ratio of P over Q started off with a value of 0, gradually increases, and moves towards infinity. And because this value changes continuously, it also covers all the possible positive numbers you can think of. So what's the implication of this? If we multiply this ratio of P over Q by a constant of minus B here, when the ratio takes value 0 at the Q-intercept here, our elasticity is going to be 0 because we're multiplying minus B by 0. Well, what is the elasticity at the P-intercept here? Well, we're multiplying minus B by positive infinity. So the elasticity is going to be negative infinity. What about in between? The constant minus B isn't changing at all. What we're changing is the ratio of P over Q that's continuously rising from 0 to infinity. So the elasticity also changes from 0 to negative infinity as we travel along this linear demand curve. And because elasticity changes from 0 all the way to negative infinity, there's bound to be a place where the elasticity is equal to minus 1. And because the elasticity at this particular point has an absolute value of 1, we call it the unit elastic point. Another way to think about the unit elastic point is that when the ratio of P over Q changes from 0 all the way to infinity as we travel up the linear demand curve, it's bound to pass by a particular point that has exactly the value of the slope of the demand curve. So then it just cancels out with the minus B here, which is exactly 1 over the slope of the demand curve. So then they cancel out with each other and left with an absolute value of 1. And that's the unit elastic point. Now, because the value of P over Q changes continuously, there is only one such a point where we're going to have unit elasticity on the linear demand curve. And moreover, we can also derive from our previous argument that because the absolute value of the elasticity is rising from 0 all the way up to infinity as we travel along this demand curve upwards, what happens is that below the unit elastic point, we're going to have an elasticity that is less than 1. And when we move above this unit elastic point, the absolute value of the elasticity is going to be greater than 1. So we'll usually say that the linear demand function is cut into two portions by the unit elastic point. Below the unit elastic point, it is the inelastic portion of the demand curve. And above the unit elastic point, it is the elastic portion of the linear demand curve. These properties sounds really abstract and somewhat obscure, but it turns out they are closely linked to firms' behaviors when they think about maximizing profits with respect to consumers' responses. And we'll refer back to these results later on. And this is simply a different graph from the textbook that shows exactly the same kind of properties from linear demand function, but using an example of the processed pork study. Once we have a good understanding of the properties coming from the definition of price elasticity of demand, what we'll realize is that there are two extreme forms of demand curves that are both linear. One extreme form is what we call a perfect elastic demand curve. And that's a horizontal demand curve where when the price changes ever slightly, almost the entire quantity demand is gone. You can think of it as a downward sloping curve that is extremely flat. So if you raise price ever slightly, the entire quantity demanded is gone. The other extreme is a vertical demand curve, which we call perfectly inelastic demand. This is where, regardless of how you change price, the quantity demanded is almost never changing. And the names of these curves are coming from the absolute value of their price elasticity of demand. With an almost flat linear demand curve, because the derivative of the demand function with respect to price is negative infinity, so regardless of the ratio of P over QD, the product is always negative infinity. This is why the elasticity is very, very high, which is referring to the intuition that we just mentioned On the right-hand side, with the perfect inelastic demand curve, it's exactly the opposite, where the derivative of the quantity demanded with respect to price is 0. And as a result of that, regardless of the ratio of P over QD, the elasticity is always 0. In other words, when you change price by 1%, the quantity demanded is going to change by 0%. So that's saying that quantity demanded is not responding to changes in price at all. So the demand is very inelastic. Now, what we have seen through the previous example was that even when we take a very, very simple demand curve that is linear, its elasticity becomes very complicated. And in fact, if we look at most demand functions, it's going to have the property that the elasticity is going to vary as you move along that particular demand curve. But in some applications, it becomes very convenient to have a demand curve whose elasticity does not change. Well, for one thing, it is kind of intuitive that in some environments, we might want to think about a demand that always responds proportionally to the changes in price. Maybe it's always a 4% decrease in quantity demanded to a 1% increase in price. Maybe it's always a 2% decrease to a 1% increase in price. Intuitively, it is very easy to think about things like this when the response is proportional and constant. And sometimes when working with data, when the environment isn't changing dramatically, it becomes very convenient to make estimations from data when you have constant elasticity. In that spirit, sometimes we would want to use a particular type of demand function that doesn't look very intuitive at first, but it's going to give us this very nice property. And this is what we call constant elasticity demand curves. These curves are coming from this particular demand function that takes the following form. It's going to be quantity demanded is equal to A, which is a constant, multiplied by price raised to the power of epsilon. And you can rewrite this particular demand function in a log-log form. And what we do is just to take log on both sides of this function. So on the left-hand side, you end up with log of quantity demanded, and on the right-hand side, we end up with log of this constant A plus epsilon times log of price. And it turns out in this particular form, the price elasticity of demand is always the power on P, which is epsilon. Now let's take this particular demand function and verify that the price elasticity of demand from this function is indeed a constant epsilon. Doesn't matter where you go along this demand curve. So how do we make this calculation? Well, although we're not looking at a straightforward linear demand curve anymore, by the definition of price elasticity of demand hasn't changed at all. It is just, again, the derivative of the demand function with respect to price multiplied by the ratio of price to quantity. So now let's do that. Break this down to two steps. We're going to take the derivative first and then multiply to the ratio of P over Q. To find the derivative, we take the derivative of the demand function with respect to P. Again, just use the definition of the demand function that we're given here. Take derivative with respect to price. A is just a constant which comes out of the derivative. We're effectively taking derivative of P raised to the power of epsilon, which again is a constant. The only thing changing is P. So now if we take derivative with respect to P, what happens is epsilon, which is on the power, comes down, and then the power is subtracted by 1. Now, once we have the value of the derivative, we're going to plug it into the definition of price elasticity of demand and multiply it by the ratio of P over QD. Now let's do that. Now once we plug in this expression into the position of dQd dP, which is here, and then multiply it by P over Q, what we have is the following. First of all, we're not keeping QD here. Instead, we're going to plug in the definition of QD, which is A times P to the power of epsilon, down here into the position of QD. Second of all, we would notice that we can collect terms because we have P to the power of 1 here and P to the power of epsilon minus 1 here. So combine these two terms, we're going to have p to the power of epsilon. Now what we have is a multiplied by epsilon times p to the power of epsilon, divided by a times p to the power of epsilon. Now, very conveniently, a and a cancels out, and p to the power of epsilon cancel out with p to the power of epsilon. As a result, what we're left with is just a constant of epsilon. Now remember, because epsilon is just a constant, any number, -2, -4, -5, it is a constant. So the price elasticity of demand is always constant, unlike on the linear demand curve. It has nothing to do with the ratio of P over Q anymore, because through the formula, the changing ratio of P over QD somehow magically cancels out with the derivative at all times, and they work out to be a constant of epsilon. We're going to see this observation a little bit better on the graph, the next slide. So with this result, we have verified our statement, the price elasticity of demand on this strange looking demand function is in fact always a constant, and it is epsilon. Now, if we plot a couple of different constant elasticity demand curves on the graph, what you will notice is the following. First of all, it's not straight. It sort of bends down like this. Second of all, what happens through a constant elasticity of demand curve is the following. Exactly by the observation we derived from the linear demand curve, the ratio of price to quantity is always going to increase as we travel up any demand curve, because it is downward sloping. So if the slope is not changing at all, the elasticity is bound to change. So how do we keep the elasticity constant? Well, it must be that the slope of this demand curve has to also change with the change in the ratio of P over Q. When the ratio of P over Q is low, we would want the demand curve to have a slope such that it is exactly 1 over the value of P over Q, so that they can cancel out with each other. When the ratio of P over Q is small, we would want the demand curve to be flat. When the ratio of P over Q is high, we would want the demand curve to be steep. And if the function is such a way that the P over Q is changing just as the slope of the curve changes, then we're going to have constant elasticity. And that's exactly the intuition working behind the constant elasticity demand curves. Now, combining these curves with our true extreme linear demand curves, the perfect elastic demand curves and the perfectly inelastic demand curve. Now let's take the thought experiment that we're starting off from a constant elasticity demand curve that has elasticity of demand equal to -1. In other words, the entire demand curve has unit elasticity. Now, as we increase price elasticity of demand, but still keep the function as constant elasticity, what happens is the demand curve will start to bend upwards on this side and bend downwards on this side. And as you increase the price elasticity of demand more and more, what happens is the startup becomes more and more elastic. The right-hand portion of this curve tends towards this flat baseline, and the left-hand side curve start to bend downwards and also tending towards this horizontal baseline. In other words, as the absolute value of the price elasticity of demand increase from 1 to 2 to 3 to 4 to infinity, the demand curve is going to tend towards this extreme, which is perfectly elastic. Well, what if we move towards the other direction? Starting from the unit elastic, constant elasticity demand curve, if we start to decrease the elasticity, if the quantity demanded is now becoming less and less responsive to changes in price, then what happens is the right side of this curve start to bend backwards. the left-hand side part of this curve start to bend rightward, they will tend towards this other extreme, which is the perfectly inelastic demand curve. And that's perfectly intuitive. We can imagine an entire spectrum of constant elasticity demand curves filling up this entire space between these two extremes of perfectly inelastic demand curves and perfectly elastic demand curves. As we change the price elasticity of demand from 0 to negative infinity, these curves just start to rotate and fill up this entire space. So you pick any elasticity, you're going to find the corresponding constant elasticity demand curve in that spectrum. Now, through the example of price elasticity of demand, we have seen two examples of how to calculate elasticity through two different demand functions. Similarly, exactly the same principle holds when we want to calculate income elasticity of demand or cross-price elasticity of demand, or even the price elasticity of supply. We just need to swap out the demand function by the supply function. Regardless of what kind of elasticity we need to calculate in the future, we're just going to follow exactly the same steps. Again, whenever we can use derivatives, we can calculate derivative first and then just multiply by the ratio. To motivate our previous example, we mentioned how convenient it is to work with a demand curve that has constant price elasticity of demand. And similarly, you can imagine that the same principle would also translate to the supply side. So, can we have a supply function that has constant price elasticity of supply? Well, of course we can. And if we look at an expression, it's going to look exactly the same, where we just write down a supply curve that has quantity of supply is equal to some constant B multiplied by price raised to the power of another constant, which is eta. And of course, it has the log form as well. If we take log on both sides of this supply function, we're going to have log of quantity supplied is equal to log of the constant B plus eta times log of price. You can verify that in fact the price elasticity of supply for this function is indeed a constant eta. And similarly, we can try to plot this function, and what we realize is that just like in the demand case, where different constant price elasticity demand curves can be thought as filling up this entire spectrum between the perfectly inelastic and perfectly elastic demand curves, you can think of exactly the same thing for the supply side. Can have perfectly inelastic supply curve, which is vertical. It doesn't matter how price changes, the quantity of supply is always constant, versus the other extreme, where the price elasticity of supply is almost infinity. Think of that as a positive slope curve that is almost entirely flat. So as you decrease the price by a little bit, almost the entire supply is gone. Now if we start to plot constant elasticity supply curves, what we'll realize is as we dial up the price elasticity of supply, these curves start to tend towards the perfectly elastic supply curve. Whereas as you dial down the price elasticity of supply, they start to bend backwards and tend towards the perfectly inelastic extreme. On its own, elasticity seems like a very obscure and strange concept. But throughout this class, and actually beyond this class, in many advanced classes, you're going to see the power of this concept. And in some data-driven classes, hopefully you're going to see how the power of elasticity allow us to make good estimates using data.